Great, thank you, Jeremy, and thanks to the NOCoE team for the invitation, and thanks to all of you here today for your time. My name is Tom Corringham. I'm an economist at the Center for Western Weather and Water Extremes here at Scripps Institution of Oceanography, University of California, San Diego. I know the major topic of today's webinar is wildfire. I'll be talking about atmospheric rivers, different topic, but related in several ways to wildfires. The main relationship being the compounding impacts of wildfire followed by storms produced by atmospheric rivers leading to debris flows. I have actually done some other work on the impact of wildfire on collisions and road safety, but my talk today will be primarily focused on atmospheric rivers and impacts on road safety and mobility in the transportation sector. I would like to acknowledge our funders at the Aurora program based at Iowa State, especially Zach Hans and Neil Hawkins for their support throughout this project. Next slide, please. So just to give some background, atmospheric rivers are severe winter storms that affect the west coast of all major land masses at the mid-latitudes, including the west coast of the United States. Like other forms of inclement weather, atmospheric rivers decrease the safety of roadways, bringing rain, ice, snow, increasing collisions, delays in travel time, and reducing, in some cases, traffic flow. So the key question that we were seeking to answer in this study are, what are the impacts and costs of atmospheric rivers to the road transportation sector? Our focus was on passenger vehicles, not on the freight transport system. And also we asked how atmospheric river forecasts could be used to reduce these costs. Our objectives were to develop a methodology to estimate the costs of atmospheric rivers and apply this methodology to focus sites in California, Colorado, and Utah. Next slide, please. Here we have a video that will show about atmospheric rivers.
Imagine a river in the sky with more than twice the water of the Amazon. It's called an atmospheric river. Atmospheric rivers are long, narrow bands of concentrated water vapor that produce major amounts of rainfall. Atmospheric rivers begin in the warm waters of the Pacific, where water evaporates into the air. When this humid air meets a Pacific storm, the water vapor is concentrated and driven toward the coast, becoming a fire hose of rainfall and wind. Once the atmospheric river reaches the coastal mountains and the inland Sierra, the collision squeezes additional rain and snow from the system. Atmospheric rivers are responsible for up to half of California's annual precipitation. Scientists at Scripps Institution of Oceanography have developed a new system that rates atmospheric rivers on a scale from 1 to 5. The rating system helps identify atmospheric rivers that are beneficial, such as those that replenish reservoirs, and ones that produce hazards like flooding. Understanding atmospheric rivers is key to improving weather forecasts for better managing water resources and predicting flood risk.
Great, thanks for that. So just to give you the headline results here, we did find that atmospheric rivers reduce road safety and mobility at our 3 test sites. We found specifically that atmospheric rivers decreased demand for road travel on California's I-5 freeway, and atmospheric rivers increased crashes, road closures, and delays at focus sites in Colorado and Utah. We also find that forecasts could reduce costs to drivers and road management agencies. Specific results in California on the I-5, we found that passenger vehicle flow decreased by up to 17% during atmospheric river conditions at an estimated cost of $135 million per year. In Utah, we considered 4 test sites, and we focused only on accident costs, and there we found costs of $9,000 per freeway mile, or approximately $890,000 per year. And in Colorado, we looked at a single month, March 2019, and found that delays associated with atmospheric rivers cost over $2 million. Next slide, please. The data that we used were road safety and mobility data from state departments of transportation, including incident reports and traffic census data. On the atmospheric river side, we used catalogs of atmospheric rivers, their incidence, and their intensity. And I should just take a minute here to describe the atmospheric river data. So unlike hurricanes or tropical storms, it is not always obvious what counts as an atmospheric river. A strong one, you kind of know it when you see it, but the weaker ones are a little bit harder to distinguish from other inclement weather systems. So there are detection algorithms, and the one that we used is known as the Guanin-Walliser detection algorithm that comes out of NASA's JPL. And this is a relative scale as opposed to an absolute scale. So atmospheric rivers can be measured in terms of the amount of water vapor that travels over a given point in space, or it can be measured in terms of the relative amount of water vapor. And in this one, we use a relative scale, which allows us to capture weaker atmospheric rivers that occur to the east of the Sierra Nevadas, so including Colorado and Utah. So our numbers for Colorado and Utah are the atmospheric rivers that were captured there were somewhat weaker than the ARs that were captured in California. So just a note there. In terms of the impact analysis, we matched the Department of Transportation data to the atmospheric river data. And this methodology that we developed, I should note, could be applied to any form of inclement weather. So if you have Department of Transportation, incident, and traffic census data, it can be matched to weather data. And it's possible using our methods to back out costs of these different weather events on road transportation networks. We conducted a statistical analysis linking these data sets, controlling for day of the week, time of day, and location effects, and we estimated the impacts of atmospheric rivers over baseline conditions. For our economic analyses in Colorado and Utah, we used estimates of delay costs and accident costs from the literature, and using the impacts of the atmospheric rivers, we were able to estimate the costs of these impacts. In California, we developed a demand model for vehicle miles traveled to estimate the costs of decreased mobility. Next slide, please. For the Colorado focus site, we chose the I-70 west of Denver, and this was in consultation with Colorado DOT. This is the major east-west freeway in Colorado. West of Denver, it extends up into the Rocky Mountains near many of the major ski resorts. So it's a very busy corridor. We used road closure data, and the data we were using included the location of the closure, the direction, the date, start and end time, type of closure. We also had data on events and event type, subtype, and closure durations. And we, in the data, there were 434 events and 98 closures. So this was over a single month. And just to think of this, there can be closures at multiple sections on the freeway, eastbound and westbound. So that's why the number of closures is greater than the number of days in the data set. And of these 31 days that we considered, 10 of them were atmospheric river days. So about a third of the days were atmospheric river days. And I should just note that March 2019 was a very significant avalanche cycle in Colorado, which is why the Colorado DOT was interested in this specific month. Next slide, please. And here we just see the I-70 corridor of interest. Next slide, thank you. So here are the key results. The table on the left shows that closures increased significantly. So full closures, there were about 2.3 on non-AR days, and on AR days, there were over 20. So that was a 9-fold, 8 or 9-fold increase in road closures. Chain restrictions were also up, general events and severe incidents were up as well. So severe incidents increased by 61%, for example. On the right, you can see the traffic flow by time of day on atmospheric river days and non-AR days. So in black, you can see a non-AR day traffic flow over the course of 24 hours. And in the red line, you can see the impact of atmospheric rivers decreasing that traffic flow. In the lower panel, you can see that decrease in blue. We used estimates of the cost of delays to get the total cost of delays here was $2 million. So this is only considering delay costs, not considering the reduction in road mobility and not including the cost of increased accidents and incidents on the road. Next slide, please. For Utah, we chose 4 focus sites, again, in collaboration with the Utah Department of Transportation. If you're familiar, you would probably recognize these sites: the I-70 at Clear Creek Canyon, the I-80 at Parley's Canyon, US Route 6 from Spanish Fork to Helper, and US Route 91 from Brigham City to Wellsville. These are all mountain passes that are susceptible to extreme weather conditions, road closures, and accidents and other incidents. For this data set, we had 7 years of data. We considered October 2012 to December 2019. We stopped before COVID as everything changed rather dramatically during COVID. So we wanted to keep conditions fairly stable across the analysis, which is why we chose that 7-year period. The data included the location of the accident or collision, the direction, freeway direction, the date, the time of the incident type, and lane and road closure duration. Next slide, please. Key results. We found that there was an increase in accidents associated with atmospheric rivers, unsurprisingly, at these 4 sites. The increase ranged from 4% on the I-80 to 20% on US 91, and the cost associated with this, again, using costs from the literature of non-fatal collisions, was $9,000 per freeway mile, an additional $9,000 per freeway mile over normal conditions, or $890,000 per year. Next slide, please. For California, so for Colorado, we looked at delays. For Utah, we looked at collisions and accidents. And for California, we wanted to look at road mobility, so actual impact of atmospheric rivers on passenger vehicle flow and vehicle miles traveled. On the left, you can see the freeway system in California, and on the right, you can see the I-5, which extends about 800 miles from the border of Mexico up to the border of Oregon. We divided it into 4 sections: Southern California, which the I-5 passes through San Diego and Los Angeles, so very busy stretch of the I-5, through Central California, which is more agricultural and less busy section near the Bay Area, east of the Bay Area, and then Northern California, which is higher elevation terrain, more susceptible to snow and ice as a result of atmospheric rivers. Next slide, please. For this, we broke atmospheric rivers into 5 categories from 1 to 5, and this is based on work that comes out of my center, our center, the Center for Western Weather and Water Extremes, or CW3E. This is similar to the hurricane scale of 1 to 5 or tornado scale of 1 to 5. In the case of atmospheric rivers, it's a location-specific categorization, and it depends on the duration and the intensity of the atmospheric river. Next slide, please. So this figure shows the impacts of AR1s through AR5s at the 4 different sections of the I-5 in California. As you move to the right, that is a % reduction in vehicle class, in the V-class passenger flow. You can see that by and large, AR4s and 5s have a greater impact. Almost all of these ARs are associated with a reduction in V-class flow. There is an exception here, Central California. For the milder ARs, actually, we saw an increase in flow, and there are a number of possible reasons for that, which I won't go into now. But I will note that the impacts were actually not statistically significant, whereas the positive impacts, the reductions in flow associated with the stronger ARs, those were statistically significant. Next slide, please. So from this, we were able to, from a similar analysis focused on vehicle miles traveled, we were able to estimate the cost of the reduction in traffic flow. So obviously, road travel has value to passengers, to drivers. And so a reduction in travel associated with inclement weather has a cost, an associated cost. And the way we worked out the cost was standard economic theory to calculate the change in the demand associated with these inclement weather events, which you can see on this figure as a shift in that downward sloping curve to the left. So on the x-axis, you have vehicle miles traveled. On the y-axis, you have the price or the value of a vehicle mile traveled. During non-atmospheric river conditions, we estimated 39 million VMT per day. On atmospheric river days, that was reduced by to 38.5 million VMT. And once you figure out the cost of this in terms of reduced what is called consumer surplus, we found that the costs were on the order of $134 million per year. And we did a sensitivity analysis where we varied the sensitivity of demand to the price of travel, and the range that we found was $99 to $295 million per year. But our central estimate was about $130 million per year cost. And this was just for the I-5. We're extending the analysis now to look at the entire California freeway system, but for the I-5 alone, cost of atmospheric rivers was on the order of $130 million per year. Next slide, please. As a final section of the project, we considered the potential value of atmospheric river forecasts to road managers and to drivers. Atmospheric river forecasts have been improving consistently year to year. From 1 to 7 days, we have pretty good forecasts of where the atmospheric river will be and what the intensity will be. And this is because we can watch the atmospheric rivers progress over the Pacific Ocean. And we actually have a program at our center where we fly Hurricane Hunter aircraft that are usually used for hurricane reconnaissance in the fall, in the late summer and fall. We use them in the winter to fly over atmospheric rivers and gather information, which allows us to accurately predict the location and intensity of atmospheric rivers up to 7 days in advance. 7 to 14 days, we can sometimes predict the location and intensity. We can usually predict whether they're going to happen or not, just not exactly where. We also are developing subseasonal to seasonal forecasts for situational awareness, seasonal projections, and using climate models, we're able to look at the long-term decadal projections of atmospheric rivers. So we know that as temperatures increase globally, that allows the atmosphere to hold more water vapor, and that leads to an intensification of most storm systems, including atmospheric rivers. The potential applications of atmospheric river forecasts and improved forecasting technology include road weather management information systems, dynamic traffic signals, maintenance decision support systems, AR warning systems, and long-term infrastructure investments for the climate projections. Next slide, please. So in terms of potential for future work, we are in the process of developing an AR operational product using our latest forecast capabilities at our center, and expanding the AR impact analysis, considering beyond just these 3 test sites, looking more comprehensively at the Western United States. It is possible that ARs have impacts in the Midwest, Southeast, and Northeast. There are ARs in these regions, but in these regions, it's usually other weather systems that cause the greatest impacts on transportation networks. So again, the models that we developed could easily be applied to these other forms of inclement weather systems. We didn't look at freight networks, but this is a possible direction for future work. And we didn't consider the broader economic impacts on local economies. So you could imagine coastal communities where roads are actually shut down along Big Sur, for example, or mountain passes to mountain communities. The impacts could be significantly increased. Next slide, please. I'll actually skip over these next 2. These are just to show the forecast capabilities that we're developing at our center. Next slide. This one, the top center figure shows the error associated with traditional forecasts, and the top right figure shows the reduction in error associated with our new artificial intelligence-based weather forecasting systems. So you can see that, well, it's not obvious from these figures, but maybe take my word for it. There are significant improvements in the forecasts associated with incorporating machine learning and artificial intelligence techniques into the forecasting methods. Next slide. The goal here is to be able to develop a tool that can be used by road managers and that can be presented to drivers to alert them to changing weather conditions. Here we see a color-coded system for I-5 showing where impacts are likely to be greatest. Next slide. This could be presented in terms of the increase in accidents, for example. Next slide. Or economic impacts. One more slide, please. So to summarize, we found that atmospheric rivers decrease traffic flow, increase accident costs, and increase delays. And these changes in the road transportation network system, these impacts can have significant costs. One more. I guess two more. Potential future work I mentioned, so expand the analysis, consider freight impacts and broader economic impacts. And next slide. I'd like to thank a number of folks at different state departments of transportation who reviewed our work, and also folks at the Aurora program for sponsoring this work. Thank you.